Welcome to another episode of AI 10X brought to you by 10 Leaves. So I want you to imagine you're driving to work.
Right, the daily commute.
Yeah, the daily commute. You're sitting in bumper-to-bumper traffic on this massive steel suspension bridge. You're sipping your coffee, listening to the radio, completely oblivious to what is actually happening deep inside the concrete pillars right beneath you.
Oh, absolutely. We just take it for granted.
We really do. I mean, for a century, we've treated those pillars as permanent static fixtures, but today's mission is to look right beneath that surface to understand this massive, kind of invisible shift happening in our modern cities.
And it really is a monumental shift.
It is. We are taking a deep dive into the hidden world of critical infrastructure. Specifically, we're looking at how artificial intelligence is stepping in to make the very foundation of our society. You know, our roads, bridges, tunnels, power grids, smarter, safer, and infinitely more resilient.
Because, we are fundamentally changing our relationship with the built environment around us.
Yeah.
We're moving away from that static concrete world we've known for centuries and entering this entirely new era where our physical world is completely intertwined with predictive intelligence.
Okay, let's unpack this, because when you think about traditional infrastructure, it really is like a stoic, silent giant.
That's a great way to put it.
Right. Think about that massive steel bridge or a concrete tunnel that burrows deep under a freezing river. By design, these structures just bear the weight of the world silently.
Yeah, they don't complain.
Exactly. They don't complain when they're tired. They don't wince when a 20-ton commercial truck slams on its brakes over them. They only ever speak up when they break.
And usually when a bridge speaks up, it's a total disaster.
A catastrophe. So how exactly is artificial intelligence giving these silent slabs of concrete and steel a voice?
Well, for all of modern history, infrastructure has indeed been completely mute. What artificial intelligence does is it finally provides a nervous system to that silent giant.
A nervous system.
Exactly. And it does this through continuous, incredibly granular monitoring. City planners are layering these structures with this intricate network of sensors.
Okay.
And then they're feeding that constant stream of massive, just totally unstructured data into advanced predictive analytics. So AI essentially gives the structure a vocabulary to communicate its stress levels, its wear and tear, and even microscopic shifts in real time.
I want to dig into the actual mechanics of that, though, because if I'm standing on a bridge when a semi-truck rolls by, the whole thing bounces.
Oh, yeah. It's terrifying if you aren't used to it.
Right. It shakes, it groans, it's incredibly loud. So how does an AI system separate the normal, everyday chaos of, thousands of cars from the sound of one actual dangerous structural flaw?
See, that is the core technical hurdle that really only AI could solve. Because we're talking about sensors that measure vibration, temperature fluctuations, material strain.
All at once.
All at once. And even the tiny acoustic emissions of concrete microfracturing.
Wait, concrete makes a noise when it microfractures?
It does. If a single steel wire inside a thick suspension cable snaps, it creates this highly specific acoustic ping.
Wow.
But, like you pointed out, that ping is completely drowned out by wind, temperature expansion, tire noise.
Just the roar of the city.
Exactly.
Right.
A human being or a traditional computer program just cannot process millions of data points a second to determine if, say, a slight increase in vibration on a Tuesday correlates with temperature drop on a Wednesday.
Or if it's just heavy traffic because there is a baseball game downtown.
Right.
Because the baseline is always changing. I mean, a bridge in the heat of summer has to behave differently than a bridge in a blizzard.
100%. So the machine learning algorithms spend months just listening and feeling.
Just learning the bridge.
Yet the AI synthesizes all of that raw, continuous environmental and structural data to establish what a healthy dynamic baseline looks like for that specific structure.
Under every condition.
Under every possible weather and traffic condition. And once it understands the unique heartbeat of that bridge, it just sits there and watches for any deviation from that baseline.
So instead of waiting for a massive crack to appear on the surface where a human inspector, dangling from a rope, can see it with the naked eye.
Which is how we used to do it.
The structure is essentially flagging a microscopic anomaly deep inside a support beam. This brings us right down from the high-level theoretical concept of smart cities to the physical reality of the roads you and I drive on every single day.
It's very tangible.
Maintenance fundamentally shifts from being reactive to being proactive.
Well, the historical approach to infrastructure maintenance has operated entirely on a schedule of reaction.
We wait for things to break.
We do. A pothole opens up, it tears up a few tires, someone calls the city, and, eventually A crew goes out to patch it.
If we're lucky.
Right. Or a bridge shows signs of advanced rusting, an emergency budget gets scrambled together, and traffic is shut down for 6 months of major renovations.
Hmm.
It is an incredibly inefficient, disruptive, and genuinely dangerous way to manage the physical world.
To put this in perspective for the listener, injecting artificial intelligence into this process feels exactly like moving from emergency room trauma surgery to preventative healthcare.
Well, that's a perfect analogy.
Because if you never go to the doctor until you literally collapse from a heart attack, that's reactive.
It's way too late.
Right. But this AI integration is like giving the bridge an MRI and a full blood panel every single second of the day.
Yes.
You are catching a symptom like a microscopic narrowing of an artery before it even manifests as chest pain.
What's fascinating here is consider how that preventative healthcare analogy scales up to the level of public safety.
Okay, how so?
Well, when a doctor catches a microscopic anomaly on an MRI, they can treat it with minor outpatient intervention, right?
Yeah, you take a pill or have a tiny procedure.
And the patient survives without ever experiencing the trauma of a full-blown medical emergency. Apply that to a submerged tunnel.
Okay, a tunnel under a river.
Water pressure is a relentless, constant threat. If AI can detect a microscopic anomaly in the structural integrity, perhaps a structural shift of 2 millimeters that humans couldn't possibly perceive through the concrete day, it flags it immediately.
Long before a single drop of water actually breaches the interior.
Exactly.
Long before the city has to trigger an emergency shutdown, cause a panic, and evacuate the tunnel.
It allows maintenance crews to deploy overnight, inject a targeted minor polymer reinforcement right into that exact microfracture, and resolve the issue before the morning commute even begins.
That is incredible.
We were removing the element of surprise from civil engineering. And when you remove the element of surprise from massive concrete structures, you drastically increase public safety.
I have to stop you there, though, because wrapping thousands of miles of steel in millions of high-tech sensors and running continuous massive predictive analytics programs in the cloud.
It sounds expensive.
It sounds unbelievably expensive. You're adding this massive, fragile layer of digital infrastructure right on top of the heavy physical infrastructure. We all know local governments struggle to just fill the potholes we already have.
Sure.
How is this not bankrupting city budgets?
So the initial integration of AI and sensor networks certainly requires heavy capital investment. There's no getting around that. But we have to look at the alternative mechanism of how cities currently spend their money.
Which is the reactive way.
Right. Without AI, cities rely on blind calendar-based sweeps. They pay massive crews of specialized engineers to physically inspect structures on a set schedule, say, every 2 years.
Just going out looking at everything.
Yes. And that means they're spending millions of taxpayer dollars sending teams out to look at perfectly healthy concrete 90% of the time.
Wow, I never thought about it like that.
Or worse, a structural flaw develops a month after an inspection.
Oh, man.
They miss it entirely, and 2 years later we end up with a catastrophic failure anyway.
So they're bleeding money checking things that don't need to be checked and then getting hit with a $100 million emergency bill when a support column unexpectedly snaps in half.
The AI eliminates that blind guesswork entirely. It tells city planners exactly when and where repairs are needed. You don't send a 50-person crew to manually inspect a 10-mile tunnel over 3 weeks.
You just send the exact people you need.
You send a specialized 4-person crew to reinforce panel 4B on a Tuesday afternoon because the predictive model flagged an acoustic emission.
That is so much more efficient.
The optimization of labor and materials alone is incredibly cost-effective. But the real savings, the truly massive reduction in costs, comes from asset lifespan extension.
Ah, the time value of the infrastructure itself.
Exactly.
Because if a bridge doesn't fall down, you don't have to buy a new one.
Let's run the math on a major suspension bridge. It might cost $1 billion to build, and civil engineers expect it to last maybe 50 years before the structural fatigue becomes too dangerous.
50 years isn't that long when you think about $1 billion.
It's a massive societal investment for a 50-year return. But if, through proactive AI-driven maintenance, finding and fixing those microfractures before they compound into systemic structural rot.
Catching the symptoms early.
Right. If you can extend the safe operational life of that same bridge to 80 or 100 years, the economics completely shift.
You literally double its life.
You have just saved the city the astronomical multi-billion-dollar cost of having to tear it down and rebuild it for decades. Extending the life of a massive asset by half a century is the ultimate cost saver.
It pays for itself.
It justifies the initial hardware cost of the sensors many, many times over.
So you aren't just paying for an IT upgrade, you are literally buying decades of extra life for a billion-dollar public asset.
Precisely.
But, okay, to keep millions of sensors constantly pinging data to the cloud and to run the servers processing those acoustic microfractures, you need an unfathomable amount of electricity.
You do. It's very power intensive.
Which means this whole high-tech nervous system is entirely dependent on something even more fragile. I'm talking about the energy systems, the power grid.
The literal lifeblood of the smart city.
Yeah.
Because if the grid fails, the sensors go dark, the predictive models halt, and the giant goes silent again.
And our sources point out that AI is revolutionizing the power grid just as dramatically as the physical roads.
Even more so in some ways.
Yeah, AI is stepping in to balance supply and demand, to improve grid efficiency, and crucially, to help integrate renewable energy into existing networks. Here's where it gets really interesting.
Okay.
I want you to picture the energy grid not just as a series of wires on wooden poles, but as a massive, incredibly delicate tightrope walk.
That's a good visual.
Every single second of every single day, the amount of power being generated by the power plants must perfectly match the amount of power being consumed by the city.
Down to the millisecond.
If supply outweighs demand, the frequency spikes and transformers literally explode. If demand outweighs supply, the frequency drops, and you get cascading rolling blackouts. It is a constant high-wire balancing act. But why is AI specifically required to handle renewable energy on this tightrope?
If we connect this to the bigger picture, if we look at how we've managed that tightrope for the last century, it relied on highly controllable power generation.
Like coal and gas.
Exactly. A coal plant or a natural gas facility is essentially a giant dial. If it's a hot summer afternoon and 3 million people turn on their air conditioning at the exact same time...
Which happens every August.
Right. The human grid operator sees the demand spike, turns the dial up on the natural gas plant, burns more fuel, and increases the electrical supply to meet the demand.
But the fuel is entirely at our command.
Yes.
You control the fuel, you control the fire, you control the power output. It's a simple linear relationship.
But renewable energy completely breaks that linear relationship.
Because of the weather.
Because it is inherently variable. You cannot turn a dial to make the wind blow harder when people need to heat their homes. You cannot negotiate with a massive storm front that suddenly blocks the sun over a 5,000-acre solar farm.
You're at the mercy of nature.
As we aggressively introduce wind and solar into our existing energy networks to meet climate goals, we are introducing massive, unpredictable variability into that delicate tightrope walk. The supply side of the equation is now constantly fluctuating based on atmospheric pressure, cloud cover, and seasonal wind shifts.
And the human demand is fluctuating right alongside it, but entirely out of sync.
Yes, the infamous duck curve.
Right. Think about the daily routine of a city. The sun is shining at its absolute brightest at noon. That's when the solar panels are pumping out maximum voltage.
Peak supply.
But at noon, everyone is sitting in climate-controlled office buildings. Peak human energy demand actually hits around 7 p.m. Everyone gets home, turns on their electric ovens, fires up their televisions, cranks the AC, and plugs in their electric cars.
And what is the sun doing at 7 p.m.?
It's setting.
It's setting.
Yeah.
The solar supply is crashing at the exact second. Human demand is skyrocketing.
And that phenomenon is the greatest challenge in modern power engineering.
Without a doubt.
Yeah.
A human operator sitting in a control room cannot manually balance a grid where the supply is shifting second by second across thousands of distributed solar panels, offshore wind turbines, and residential battery systems.
It's just too much math.
There are simply too many variables. This is where AI becomes the absolute crucial synthesizer. AI can absorb massive amounts of meteorological data, satellite feeds, radar, wind speed sensors,
Weather data.
alongside historical human consumption patterns and real-time sensor data from across the city's infrastructure.
So it's looking at the weather report, but on a hyper-local, millisecond by millisecond scale.
Exactly. It can predict, with staggering accuracy, that a specific density of cloud cover will drop the output of the Western solar array by 15% at exactly 2.14 p.m.
That's crazy.
And simultaneously, it calculates that a sudden 2-degree drop in ambient temperature will increase residential heating demand by 10% across 3 specific neighborhoods.
So it sees the imbalance, like the wobble on the tightrope, before it actually happens.
Because it sees that wobble coming, it can autonomously take action.
Yeah.
It can route stored energy from massive lithium-ion battery banks or slightly adjust the output of a backup natural gas plant, perfectly smoothing out the variability before the frequency of the grid even dips.
Wow.
It acts as an invisible hyperspeed conductor, ensuring that the violently fluctuating green supply perfectly meets the real-time demands of the city.
It's doing this all entirely on its own.
Yes. Without AI managing these microsecond adjustments, integrating large amounts of renewable energy into our existing grids without causing daily, catastrophic rolling blackouts would be mathematically impossible.
Just impossible for a human.
It is the only way to maximize grid efficiency while transitioning to cleaner power.
You know, it is genuinely wild to think about the sheer amount of invisible predictive calculation going on just so I can flip a light switch in my kitchen and not even think twice about it.
We really don't appreciate it.
Millions of lines of code predicting the movement of a cloud, routing power from a battery halfway across the state just to keep my lights on. We are essentially offloading the massive cognitive burden of running a complex society to these intelligent systems.
Yeah.
Which brings us to a major realization when you look at all the sources we've discussed today. When you step back and look at the whole picture, from the AI detecting a microscopic fracture in a concrete tunnel, to the AI perfectly balancing the output of a solar farm with the evening commute, there's a profound shift in how we define our built environment.
We are looking at a fundamental redefinition of what infrastructure actually is.
Hmm.
Because for thousands of years, a road was just a rock you walked on.
Right. AI isn't just a shiny new diagnostic tool for maintenance crews to use. It is taking our infrastructure and shifting it from something that passively supports society into something that actively learns from it.
It's an active participant now.
The bridge isn't just silently holding up cars anymore. It's monitoring how traffic flows on a Friday afternoon. It's sensing the weight distribution of commercial trucks and dynamically adjusting its own structural health profile based on that localized data.
And the grid is doing the exact same thing.
Yeah, the power grid isn't just blindly pushing electricity down a wire. It's learning our deepest behavioral habits, like when we cook, when we sleep, when we charge our devices, and optimizing its physical routing to serve us better.
It is the difference between an environment that we simply exist within and an environment that is dynamically reacting to our presence.
A two-way street.
The city itself becomes a learning organism. It observes human behavior, it predicts our needs, and it adapts its physical and electrical reality to match us.
It completely changes how you look at the concrete and steel around you. The city is awake.
It really is.
We're going to be continuing this journey into the ways artificial intelligence is reshaping our physical world. Next time, we'll be taking our deep dive into the skies, exploring the massive role of AI in aviation and how it's changing the way we fly.
That's going to be a good one.
But before we wrap up today, I know you had a thought on this idea of a learning city that really flips the script on everything we just talked about.
Yeah, this raises an important question that I think we all need to mull over as we watch these systems come online.
Okay, lay it on us.
We've established that our smart infrastructure is constantly learning from our behaviors. It is ingesting our traffic patterns, our daily routines, and our energy use to perfectly optimize itself for the way we live today.
Right.
But what happens to our cities when human behavior undergoes sudden, massive shifts? Think about a global event that, overnight, changes how millions of people work and travel.
Like a sudden shift to remote work.
Exactly. Or a sudden technological breakthrough that entirely alters the nature of the daily commute. Will our highly trained, deeply integrated smart infrastructure, which has spent years learning the old baseline, be flexible enough to quickly unlearn its assumptions and adapt to a radically new reality?
Oh, wow.
Or will we find ourselves living in cities that are perfectly flawlessly optimized for a version of society that no longer exists?
That is a haunting and fascinating question to leave off on. If the silent giant learns the wrong lessons, how do we teach it to forget? This was another episode of AI 10X brought to you by 10 Leaves.